teams. We have CYWU, Lelouch, Pixie, YHK, and DD are the top 5. So would a representative of the top 5 teams come and grab your tasty reward? Yeah. Oh yeah, these are individual. So would the top 5 individuals please come and grab their reward? All right, so we're missing, there we go. Excellent. So congratulations. And all right, so now let's get back to duality. Which is what we were discussing at the end of class last time. So the point of duality, like we were talking about, is to take one optimization problem, the primal, and transform it to another one, the dual, in a way such that it's equivalent. In other words, the solutions give you basically the same information and the value is equal, but you get a fresh look at the optimization problem, right? So the idea is that it can help you design an algorithm to be able to, if you take a look at the dual. So, you stare at the primal for a long time. You absolutely can't figure out what the right algorithm is to solve it. So you take the dual and you get a fresh look. OK? So any questions that anybody has that they remember from last time? Yeah?
So the primal problem is usually formulated for real-world application, so it can be interpreted with spectrum. How about the dual problem?
Right. So the question is interpreting the dual problem. So when you make the primal problem, you usually did it for a reason, right? You had some real-world application you were trying to solve. So you for example, made a likelihood optimization for some model. And then the question is, how do you go about interpreting the dual? So in part, it's problem dependent, but there are a couple of tricks that work in general. The most useful is to think of the Lagrange multipliers as either forces or costs, right? So there's one Lagrange multiplier per constraint of your primal problem. And you can think of that Lagrange multiplier in one of 2 ways. Either how much is it costing you to have this constraint, or in other words, how much would you pay to have this constraint relaxed a little bit in order to get the optimum a little bit better. And then the other one is as a force, right? So if you have some constraint here and the optimal solution is tied up against the constraint, you can think that the constraint is pushing back with some amount of force against the solution to keep it from moving any farther. And either one of those 2 interpretations might be better depending on the problem. But those are the 2 sort of main domain-independent ways of getting an interpretation of the dual. Other questions? All right, so we had, just to summarize what we were doing, so let's suppose we started with a minimization problem with some constraints. What we did was we introduced one Lagrange multiplier per constraint. If we had an equality constraint, that led to an unbounded or a free multiplier. And if we had an inequality constraint, that led to a non-negative multiplier. And then we used the identity that the sum over all constraints I of the ith multiplier times the ith constraint, that has to be greater than or equal to 0, right? Because for a feasible thing, the value of the ith constraint has to be greater than or equal to 0. You can have a free multiple if you have something that has to be positive. Right? Use that to get a bound. And the way we got a bound was by subtracting it from the objective. So for a linear program, we had that the objective was C transpose x for some constant vector C and a vector of variables x. And we bounded that by C transpose x is greater than or equal to C transpose x minus the sum of the multipliers, right? Sum of the multipliers times constraints, which was going to be, in this case, lambda transpose ax minus b, right? So this thing here, we know that it's positive, so if we subtract it, it gets less, right? And so this makes sense as a way to get a bound on the objective. Right? And then we did the same thing for a quadratic program. We did, in that case, the objective was C transpose x plus x transpose hx over 2, right? And that was greater than or equal to C transpose x plus x transpose, x transpose hx over 2 minus lambda transpose ax minus b, right? And then we guessed a constraint on the Lagrange multipliers. Last lecture, I didn't give you any intuition about how to guess that constraint, but I'm going to do that later today. For a linear program, we guessed that the Lagrange multipliers lambda satisfied this equality. And for a quadratic program, it was the same equality except with h non-zero, right? So the only difference between a linear and a quadratic program is that the quadratic part, the Hessian matrix H, is non-zero. Okay? And given that constraint on the Lagrange multipliers, we substituted that in, did a bit of manipulation, and got an optimization problem in terms of lambda. And then the dual was to find the tightest lower bound subject to all of the constraints that we had assumed, right? So the tightest lower bound means the maximum value of the dual objective, right? Because you're trying to lower bound something, you want to push up as far as possible. All right? Does that all sound familiar? Do people have questions about that from last time? All right. So it sounds there's this thing called the Lagrangian, which helps you get an intuition of the primal and the dual problems. So let's go ahead and derive that. So we have, here's a standard quadratic program with some inequality constraints. We have a vector of Lagrange multipliers, which we're going to assume are non-negative. The sum of the multipliers times the constraints is, again, lambda transpose ax minus b, right? So these constraints are the same as ax minus b is greater than or equal to 0, right? So lambda transpose times something positive, non-negative has to be non-negative. And so we had that the objective, this is the same thing that I wrote on the last slide, is bigger than or equal to this thing, minus lambda transpose ax minus b, right? Right, so this was greater than or equal to 0, and that was what allowed us to conclude this inequality. So this thing here, yes, thank you. So this thing here is called the Lagrangian. After that happy-looking guy that we had a picture of in the last lecture. And the nice thing about the Lagrangian is that it's going to give us a better understanding of both the primal and the dual problems, and it's going to help us derive those guesses that I did without motivation last time around. All right. So here's this is just a copy from the previous slide, right? The primal objective is greater than or equal to the Lagrangian, which is a function of both the primal and dual variables, which was this thing. And this inequality holds whenever we have a feasible point x and for any Lagrange multipliers that are non-negative, right? And so we can think of both the primal and the dual problems as trying to find an x and a lambda that make this inequality tight. Why do we want to make the inequality tight? Well, we want to push down on x to get the best possible x. We want to push up on lambda to get the best possible lower bound, right? And in the end, if we solve both problems, they're going to meet in the middle. And we'll have the primal value will be pushed down to the primal optimum. The dual value will be pushed up to the dual optimum. And we'll get that the lower bound that we compute is tight, right? And so it turns out then that from the Lagrangian, you can get both the primal and the dual optimization problems using this intuition. So if we minimize over x and maximize over non-negative lambda, the Lagrangian, we get the primal problem. And if we do the exact same thing but swap the order of the min and the max, we get the dual problem. And I'll actually work through that in a couple of seconds. But you know, these two things, they're almost the same. And it's a theorem that they get the same value for linear and convex quadratic programs. That's called strong duality. But does this procedure make sense, right? That we're going to take the Lagrangian and we're going to min-max it or max-min it to get the primal and dual problems. All right. So
It's not always monotone, right? In terms of x and lambda. You have a lambda times x second term.
right. So this is not the Lagrangian is not a convex function of x and lambda because it has a bilinear term in x and lambda. But for any fixed x, it's concave in lambda, so you can maximize it. And for any fixed lambda, it's convex in x, and so you can minimize it. Right? And solving them both at the same time, it's not obvious that you can do that efficiently because of this lack of convexity, but it turns out that you can for Lagrangians that come from convex programs. So that's a good question. Other questions? All right, so you might have noticed, or you might not have, because I snuck it by, that here in the primal, I didn't include the primal constraints ax greater than or equal to b, right? And the reason I skipped them is that it turns out that ax is greater than or equal to b is actually implied by the rest of the definition of the primal. So let's take a look and see why that might be true. Suppose that we violate the constraints in the primal, right? Suppose we have some component of ax minus b that's negative, okay? So here, when we do the maximization over lambda, what's going to happen? Right, exactly. Somebody said negative infinity, right? So if you have a negative component of ax minus b, let's say it's the ith component, then we can take lambda I and we can make it very large, and that's really bad for the maximization, right? It makes the value of the Lagrangian very negative. And so the optimal value of this min-max problem, it can't ever happen when there's a constraint, a primal constraint, an ax greater than or equal to b that's violated, right? So this, it implies ax is greater than or equal to b. Okay? So then suppose that that's satisfied, right? So we know ax is greater than or equal to b. Sorry, lambda goes to plus infinity, right? And the value of the Lagrangian goes to minus infinity, right? Because this is a negative term, right? You subtract a positive term and it's negative. Okay? So that's a good question.
Doesn't it go to the Lagrangian goes to infinity because ax minus b is negative, minus positive, and you subtract. And that's why it's a problem because you're maximum.
Right. Yeah, exactly. Sorry. The Lagrangian goes to, thank you. It's always good to keep the professor's signs in order. Make sure that the XOR of all of the signs is correct. You're right. So the Lagrangian goes to plus infinity. That's really good for the max over lambda, really bad for the min over x, right? And so when you're taking the min over x, you're never going to set x to something that violates the constraints, because then when you max over lambda, the Lagrangian will go to plus infinity, and it'll be really bad for the min. Thank you. OK, so now we're min-maxing. We know we have to satisfy these constraints in x. If we just set lambda equal to 0, right, this term vanishes. And so we'll be minimizing the primal objective subject to the primal constraints, right? And so therefore, we get this just gets the primal problem, right? So then the other way, for the dual, because we've dropped all of the constraints on x, right? X is a free variable. We can minimize by setting the derivative with respect to x to 0. So the derivative of the Lagrangian with respect to x, dl dx, we're going to set that to 0. And that's equal to c plus hx minus a transpose lambda, right? And here, this is the constraint that I had to guess before, right? So I've just now derived the constraint that I have to guess. So now this becomes a constraint in the dual. We already had lambda greater than or equal to 0 in the dual, right? And then if we substitute that this is equal to 0 in the Lagrangian, right, then we get that the Lagrangian is equal to, well, we get, we get x transpose times c plus hx minus A transpose lambda, right? Plus now we have a lambda transpose B left over, right? And this gets us X transpose HX, whereas we're supposed to get X transpose HX over 2, so we have to subtract minus X transpose 8. Man, I can't write today. HX over 2, right? So now we've rewritten the Lagrangian by factoring out the thing that we know to be 0. This thing goes away. We get lambda transpose B minus X transpose HX over 2. And the problem becomes to max over lambda greater than or equal to 0, lambda transpose B minus X transpose HX over 2. And then we have to have C plus HX minus A transpose lambda is equal to 0. And this was the dual problem. Right? So, so I've just argued now for both the primal and the dual that we can derive them from the Lagrangian. And the benefit of doing that was that this constraint, which was previously a mystery, is now justified. Right? We're actually solving this minimization problem over X. Does everybody get that? Any questions? Are there no questions because everybody is confused, or are there no questions because it's all obvious? Yeah.
Probably a bad question. Are we simultaneously minimizing and maximizing with respect to the success variables, or are they sort of sequential?
Right. So this means sequential, right? So you minimize over X the function max over lambda of the Lagrangian, right? Or you max over lambda the function min over X of the Lagrangian, right? So in here, the lambda player goes first and the X player gets to react. Here, the X player goes first and the lambda player gets to react. Right? And so that subtle difference is the only difference between the primal and the dual, right? The order of whether you're minimizing or maximizing with respect to X or lambda first or second. Yeah?
But are you guaranteed to get the same answer both ways?
Right. So in this case, you are guaranteed to get the same answer both ways. The theorem that says that that's true is called strong duality. And we're not going to prove strong duality, but it holds for linear and convex quadratic programs. It doesn't hold for every convex program, but it holds for a lot of them, and many of the ones that you're going to see in practice. Yeah?
How do you get from equation on top to equation in the middle?
From the equation on top here, this one, to this one here,
To the dual
to the dual. This is the definition of the dual.
at the right side.
This one, oh, I see, right. So what I did was I pulled out X transpose C plus HX minus A transpose lambda. I pulled this term out of this here, right? So I've got the C transpose X, which is this guy, right? I've got X transpose HX minus X transpose HX over 2. That gives me this term. I have X transpose A transpose lambda negated, right? That's this term. And I have a lambda transpose B, which is that term.
Why is C transpose X equal to X transpose?
Y is, I'm sorry?
Because on top you have C transpose X.
C transpose X, right? And X transpose C, those are both scalars. They're numbers. And so the transpose of a number is equal to itself. That's a good question, right? So I ignored the fact that for all of these things, all of these terms are single real numbers, and so transposing them does nothing. Was there another question? Yeah.
You were saying, so for linear and quadratic programs, the dual and primal will converge to the same thing. If you had something that wasn't one of those and it still converges, does that mean it's isomorphic to a linear program?
So the question is, what does it mean if you get strong duality in some optimization problem other than a linear or quadratic program? It's not necessarily equivalent to a linear or quadratic program in that case. There are other classes for which strong duality holds. There are other big classes for which strong duality holds. So linear and quadratic programs are a pretty big and useful class of problems.
So for instance, the
semi-definite, the set of semi-definite matrices, we talked about it a few times before, so basically primal matrices, that forms a Helm cylinder, and so there you can also have strong duality under suitable conditions, and that's an alternative and quite commonly used setup where people use convex optimization. Yeah.
Right, semi-definite programs make another great example. And in general, any cone program, so semi-definite matrices are a cone, any cone program you can get strong duality under some mild conditions. If you've heard of Slater's constraint qualification, that's one sufficient condition for strong duality to hold. Basically, it means that there's a strictly feasible point in both the primal and the dual. So more questions about the Lagrangian? All right. So we had a bound, right, from our duality. We had our objective here on the right-hand side. On the left-hand side, we got a bound, which was the dual objective, right, for any feasible dual point. And so we know that by finding a dual feasible point, we can get a lower bound on the primal objective, right? Now, what happens if this inequality becomes an equality? In other words, we have a dual feasible point with some value, a primal feasible point with some value, and those two values are equal, right? What does that mean?
There is no gap between
There's no gap between the primal and the dual solution. So the primal solution must be, I heard somebody say optimal. Yes, the primal solution must be optimal, and the dual solution must also be optimal, right? So here, right, if we have two feasible, a primal solution and a dual solution that are both feasible and they have the same value, we know the lower bound is tight, right? We've actually found something which must be optimal, and we found a dual solution that must be optimal, right? So, right? So if these things are true, we must have optimal both primal and dual solutions. These conditions together are called the KKT conditions, Karush, Kuhn, and Tucker again, for inequality constrained linear or quadratic programs, right? And they're pretty important, right, because they give you a way to check whether a solution is optimal, even if you didn't solve the problem yourself, right? So it's a good way if you go and you hire some crazy startup company to go and solve your optimization problem for you, and they come back and they say yes, the optimal value is 3.7, right? How do you check their work? Well, you ask them to give you the primal and dual feasible solutions that they came up with, and if they satisfy the KKT conditions, which are much easier to check than solving the optimization problem as a whole, then they must be right. They're not conning you and trying to get money for their IPO or whatever. So KKT is important and useful. For linear programs, it's exactly the same except that the matrix H is 0. And so that gives us that lambda transpose B is equal to C transpose X. And by rearranging this, I'm not going to do it here. Actually, no, I'll do it here because it's pretty nice. We know that C is equal to A transpose lambda, right? So I'll write that here. C equals A transpose lambda. That's this with H equal to 0. So we substitute C here, and we get lambda transpose AX, right? C equals A transpose lambda, so just substitute, we get an equality. And so that says then that lambda transpose AX minus B is equal to 0, right? That's just subtracting these two sides from each other. So what does this mean? We know that lambda is bigger than or equal to 0. We know AX minus B is bigger than or equal to 0. Their dot product is equal to 0, right? So every term in their dot product, right, the ith component of lambda times the ith component of ax minus b, that's all non-negative, right, because lambda I is non-negative, ax minus b, the ith component is non-negative. So that means then that for each I, for all I, lambda I times ax minus b, the ith component, has to equal 0, right? Because the only way for the sum of a bunch of positive terms to be 0 is for every term in the sum to be 0. Right? So what does this mean? This is a condition that's called complementary slackness. And what it means is that for each one of the constraints, at most one of the Lagrange multiplier and the constraint value can be non-zero, right? The only way for this to be 0 is for lambda I to be 0, or ax minus b I to be 0, or for both to be 0, right? And so it means the two vectors are complementary, which means that their non-zero components are in different locations, right? And so this turns out to be a very useful characterization of the linear program optimal, because it tells you something. Each one of the Lagrange multipliers tells you something about which ones of the constraints hold exactly, are tight, are binding, and which ones of the constraints are loose and could be dropped without affecting the optimal solution. Right? If the Lagrange multiplier is positive, that means that the constraint has to be tight and it's important, it's active at the solution. And if the Lagrange multiplier is 0, then you can drop the constraint and it won't affect the value of the solution. All right? So questions about the KKT conditions? Yeah?
So what is exactly optimal here? We are anyway finding the solution even if it's not equal, right? So what are we optimizing here?
So KKT are not an optimization, right? They're a set of equations that you can check. And the point is that if you do the optimization, the KKT conditions make a quick way to check that there wasn't a bug in your optimization software, right? And they also help you interpret the value of the primal and the dual, the solution of the primal and the dual, right? So the KKT conditions, sometimes you can solve them directly. For simple optimization problems, you can solve the KKT conditions directly. For others, you have to run some sort of code to solve the optimization problem, and the KKT conditions just make a way to check or interpret the answer. Right? And in particular, this complementary slackness condition, which seems kind of strange at the face of it, is useful when you're interpreting things because it lets you say which constraints were important in the optimization problem. More questions? All right, so we're almost done. I'm not going to do this, but I wanted to point out, so I brought up Newton's method for equality constrained problems. So now we can do it another way, right? We can solve the same problem another way. We can say a quadratic program with only equality constraints and only free variables. That's the same as just minimizing a quadratic subject to linear equations. And if we write out the KKT conditions for this optimization problem, it's going to turn out that we get exactly the Newton's method that I wrote out a lecture or two ago. So if you want to check your understanding, that would be a good exercise to go through. The other thing I wanted to say is that all of this you can extend to more general optimization problems. There's duality, there's a Lagrangian, there's KKT conditions for semi-definite programs, second-order cone programs, a ton of other more general convex problems. We're not going to do that now, but it's useful to know, and if you ever run across problems like these, you can look up what the duality relations are, and they'll help you solve it. The other thing that I wanted to mention is just we've spent a long time telling you how to solve optimization problems. They come up all over the place in machine learning. That's why we spent the time telling you. Here's just a list of the first 10 of them that came to my mind, right? So lassos, a particularly important one. That's L1 penalized linear regression. There's a logistic version, which is also a convex problem. Support vector machines, we're going to become a lot more familiar with them in about 10 minutes. There's robust regression, or Huber regression. So this is to deal with outliers in a regression. There's a convex problem that you can solve to do that. Group lasso, graph lasso, manifold learning, getting rich by optimizing your investment portfolios. A guy named Markowitz won the Nobel Prize for that. They're all over the place. So this is why it was important to have attention. It may be too late to go back and pay attention if you weren't already, but this is why you should have. And then the last thing that I want to say was just briefly, there's a lot of different algorithms that you can use to solve these things. Simplex is the most famous maybe for linear programs. There's a lot of gradient-based methods. So some of the best lasso solvers are accelerated proximal gradient. There's also stochastic gradient or just plain proximal gradient. Those are all good. And like we said, don't implement simplex or interior point by yourself if you have the option, right? I have done that. It was mostly a mistake. CMU has Cplex licenses, use them. Particularly simplex, there's a gazillion special cases that will bite you if you're not familiar with the implementation. All right, so that was all I wanted to say about the optimization problems. Before we turn it over, are there any questions? Yeah.
Most of these optimization problems, we are trying to find a minima in some space, and they guarantee for a local minima. Is there anything which guarantee for a global minima?
So because these are convex problems, all local minima are global minima. And so the KKT conditions guarantee you that you find a global minimum, right? If you're doing a non-convex optimization problem where there might be multiple local minima, you can get an analogous thing to the KKT conditions in the neighborhood of a local minimum. And you can analyze it that way. But for all of these things, right, it's really important that these problems that I showed you, you can set them all up as convex optimizations so that there's a single global optimum, and you can write code to find it. Right? Yeah. Semi-definite program. Linear program, quadratic program, semi-definite program. The other one that you might run across is a second-order cone program, SOCP. Yeah.
So the KKT conditions will hold even when non-convex,
They'll hold locally in the neighborhood of a minimum. For anything that's convex in the neighborhood of a minimum, you'll be able to find the KKT conditions in that local neighborhood. All right, I think that's it. So let's swap to learning about support vector machines.
Can you check the level? Okay. Test 1, 2, 3. Okay. Okay. What? Okay. Seems to work. Not very bright. Okay, well, there's nothing I can do. No, it's just the brightness level is trying to be too smart for its own good. Okay, so welcome to the second half of this lecture, and will be now putting all these cool optimization techniques that Geoff talked about to you guys last week to very good use this week. And so this might then explain a little bit more why on earth were we doing things that are essentially optimization and mathematical programming. After all, you enrolled in a class for machine learning, and we've been inflicting all this math on you, right? That horrible. Well, it's actually fun for us, but it might not have been what you expected. So this, I hope, will convince a little bit that, hey, all those things were super useful. Okay, so support vector machines. Yeah, I just thought probably one of the most hilarious explaining why a large margin separator is sometimes a useful thing. Okay, so let's go to something politically more correct. Let's say we separate ham from spam. Already looked at the perceptron, and the perceptron would find us a linear separator between ham and spam, right? And there was no guarantee which one you would find, right? You could find this one or that one. You could find another one. Okay, one more. So okay, so just looking at those 4 different separators, who would rather pick the red separator if you had to go with one? Nobody. Who would pick the purple separator if you had a choice? Who would pick the black separator? Yeah, you've already seen the slides, right? And I guess nobody picks the yellow one. Okay, but at least everybody's awake. So if you squint at that hard enough, you see that the black one is actually the largest margin separator. So essentially, this is like inserting a hyperplane and then pushing it out to either side as much as you can. And remember, 2 weeks ago at the end of the class, we already went through the optimization problem for it because I said, well, we're actually going into all the depths of optimization. Well, at least let's wait a little bit where it came from. And so remember, what we had is that we said, well, the spam, green spam, this case, red ham, right? You want to have w dot x plus b less equal than -1, and for the ham, w dot x plus b greater or equal than 1. Okay. And so if you do this, well, you can clearly see that there must be some points that sit exactly on the boundary. And for those, this function is going to be either 1 or -1. Well, I can always make it so that there are points for which this function is 1 or -1. Why? Can somebody tell me why I can always make that happen? Okay?
I can scale W and B as I like.
Correct. So I can multiply W and B, and on top of that, I can always add something to B. So adding to B shifts that hyperplane to the left or to the right. Scaling W and B jointly makes, in fact, one narrower. Okay. So those are the 2 knobs that you can play with. And so, of course, you can just go and work out what x plus minus x minus, right? Let's say this is x plus, this is x minus, and I want to measure that distance here. So all I do is I take the inner product between this and the normal vector. So I need to write w divided by the norm of w. And I have to divide by 2 because, well, it's the margin on the left and on the right. Okay. And so I get this expression here. And I know that this here is 1, and this here is -1. So it's 2. So I have 1 over norm of w. So this should be utterly unsurprising to you because we already went through this. So therefore, I can write out an optimization problem which is maximize 1 over the norm of w over w and b subject to, well, this linear constraint. Is this a convex program? No,
but I can turn it into a convex program by modifying it slightly. So the only modification is this one here, that I switch 1 over the norm of W to 1/2 norm of W squared. So the important lesson to take home here on this aspect is you may sometimes have optimization problems. Sometimes the solution can also be found by a convex optimization problem. And, well, you probably still can, but probably by now a lot of other people. You can basically take non-trivial optimization problems, rewrite them as convex problems, and then solve them optimally. And there's basically, a very large set of tools you can have access to in this case. So in many cases, it's to your advantage to solve the convex problem. There are some cases where doing that is not necessarily the most effective way to do it, but these are very special cases. So in general, reformulate. Any questions? Yep.
So going from the max to the min, that's just something that you're looking at it, you know that works, or is that?
Okay. Well, okay, so let's think about it. For this to be large, right, this has to be small. So therefore, if I don't change the constraints, whether I maximize the 1 over the norm of W, or whether I minimize the norm of W is the same thing. Now, we know that this is non-negative, so whether I take the norm or the norm squared doesn't really matter. So I can do that too. Mind you, it would be a convex optimization problem even without the square. It's just that once I square it, it becomes so much easier to solve. Because then it actually becomes a quadratic program, whereas before, it's just a norm constraint problem. I mean, yeah. So I could write minimize the norm of W subject to yi xi dot W plus yi greater or equal than 1, right? I could do that. And, well, that would be a run-of-the-mill convex program, except that, okay, let me zoom out a little bit, except that this problem now would not be particularly easy to solve. I really apologize for the horrible image quality here. I don't know how to adjust the background brightness level here. Sorry. Yeah, actually, if somebody has something dark, let me do this. This will fix it. Okay. Wallets are good for that too, right? Okay, so when you design a self-calibrating algorithm, make sure you get all the boundary cases right. But basically, this is clearly a problem that is not so much fun to solve because, it has a non-differentiable part here in the middle, right? So it has this, right? Even just in one dimension, it would already be not so much fun. So this is why you want to really transform it into this. This is much easier to solve. Okay. So now what we're going to do is we're going to compute the dual of that problem. After all, this was the entire point of last week and of also this morning. Let's look at the Lagrange function and let's go and happily compute away. So, we've, after all, invested a lot of time. Let's do that. So the Lagrange function is, in this case, well, we have the objective, so that's 1/2 W squared. And now we have all those constraints. And we first want to bring our constraints into normal form, right? So we have basically yi, well, x times xi dot W plus b minus 1 greater or equal than 0. And then I subtract them from the objective multiplied by a suitable Lagrange multiplier. So I have basically sum over alpha I and then the constraints. Who of you has done theoretical physics? Okay. Or mechanics, basically, where you had to compute virtual forces. So the civil engineers here might know this stuff. Okay, I don't know. This year we don't have any civil engineers here in the class. Oh, cool. So you would know all the virtual forces and things when you have constraints, when you don't want your bridge to crash and burn. So effectively, those alpha i's amount to forces that keep, well, the constraints satisfied, which basically push the parameter vector inside the space of feasible solutions. So if you think about it, here's what's happening. Well, this constraint here is just a half-space constraint, right? It basically says my parameter vector, so the W and B set together, must not lie on this side of the boundary. This is one particular xi, yi pair. Let's say x1, y1. They impose that constraint. Maybe x2, y2 impose this constraint here. And, well, maybe x3 imposes this constraint. And maybe x4 imposes this one here. Note, it doesn't have to be closed here. So what I then have is, I also have, so these guys, keep on pushing it, well, make sure that you're inside that feasible region. Now I then apply an objective function which, well, in the simplest case might be something like this. And there the optimal solution is easy to find, right? It's here. And it's actually entirely unconstrained. In practice, that's not what's going to happen, because in practice, my minimum is going to sit somewhere out here. And now I actually need another color for a pen. Let's say this was my objective. This is the minimum. This is W squared. So let's take a contour plot. And what will now happen is that I will get my solution here. And that means that the corresponding set of points, xi, yi, so that observation that corresponds to this boundary, will become a support vector. So this is now just looking at the entire optimization problem in constraint space. Because of course the solution would want to get here, but it can't because there's a constraint. Okay, oh my god, the brightness level is really awful. Let's brighten it up with something black. Okay. I'm not sure it helps, but okay. So now we have these constraints, and well, then what we have to do is just mechanically go through it, take the derivatives with respect to W and B, and we get equations for W and B out of it, and then we can get rid of the W's and B's and see whether the optimization problem in the alphas looks nicer. Okay. Any questions about that so far?
You said
Yep.
that observation is going to be a support vector, but what does it support?
So a support vector is going to be one of these points, one of those yellow points, right? So, sorry for not defining this. The points that are exactly on the boundary, so these are points that effectively support the definition of this hyperplane, will be called support vectors. More generally, points later on, we'll see that, well, we'll basically make this boundary rather porous, that are on the boundary or beyond the boundary on the wrong side, they will be called support vectors. Thanks. Any more questions here? Yeah?
So is that sort of mean you can think of it as each point is a constraint and those
Correct.
are the constraints?
Exactly. That's exactly this picture here. Well, by now it's really messed up, but that's how we started, right? Each of those boundaries was an observation. So this is starting to look in the dual setting where, the largest hyperplane is now minimizing a function, making sure that I on a particular point restricts the set of parameters that you should be choosing. Okay, good. So now we have the Lagrange function, right? And we just go derivatives. It's very straightforward. So taking derivatives, well, dw of 1/2 w squared is w. Right? Nothing special happened here. The derivative of a linear function, well, that's just a parameter. Seen those things before. Derivatives of vector-valued functions. Everybody's comfortable with that? Okay, good. Sorry for asking, but in some years I get people are surprised. Okay, there's nothing wrong with that, but anyway. So dw of dl db, so that's basically the constant offset. Well, that just gives us sum over alpha I yi. So these are those two equations right here. Yeah, these two. Okay. And now if you look at them, you can already see something very interesting happening. Well, they need to be satisfied, of course, but that means I can just compute w equals sum over alpha I yi xi. Does that look familiar from something that we did in the past? Okay. Exactly. The perceptron had exactly the same expansion. The only difference was that rather than alpha I being general Lagrange multipliers, the other alpha i's were either 0 or 1. They were 0 if things were classified correctly. They were 1 if they were classified incorrectly. Now, in this more general case, they'll be 0 if they are classified correctly with a non-trivial margin, and they are greater than 0 if they are not classified with that margin or just on the boundary. And we get another interesting condition, namely sum over alpha I yi equals 0. And this is really where physics intuition is kind of useful. As remember, we had this boundary. And we had the Lagrange multipliers basically making sure that everything is properly classified. So sum over yi alpha I equals 0 means the guys pushing from the left and the guys pushing from the right have to have their forces match exactly. That's basically what this means. The other useful thing in this context is you can see that, so while b was a free variable before, and w likewise, these two free variables turn into an equality constraint. And furthermore, the inequalities that we had before, well, we still have them because we still have the condition that the alpha i's have to be greater or equal than 0. So free variable becomes an equality constraint. As it turns out, an equality constraint becomes a free variable, and inequalities turn into inequalities. So it's an easy way of generally checking whether, after you've done the dualization, whether you've gotten everything right. It's very easy to just mechanically go through it and check this. Okay? So now that we know this, we can just plug those terms on for w and b back into the Lagrange function, right? So, and if you do that, you get this equation. So do you want me to derive that step? I can do that on a piece of paper. It's no big deal. Would you like me to do that? Okay, good. Let's see. So remember we had the Lagrange function L being 1/2 norm of w squared minus sum over alpha I yi xi dot w. And then we had minus sum over, plus sum over the alpha i's. And we also had minus sum over alpha I yi. I've just expanded that last bracket already. Yeah, there should be. Correct. So now if we look at the derivatives that we got, we can already identify a few terms. Sorry, my hands are too bright. Okay, let's see whether that helps. Yeah, we need to ask AV staff. So if you look at this, you can see that this is already W. You can already recognize it exactly from the condition that we had before. Because we can see that W equals sum over alpha I, yi, xi. Okay? Well, nothing changes here. But we know that this term here equals 0. So we get equals basically minus 1/2 norm of W squared plus sum over I alpha I. And now I just plug in what I know about W. So this is then minus 1/2 sum over I and j alpha I alpha j yi yj xi xj plus sum over I alpha I. Okay. Everybody cool with that? Which is exactly the optimization problem here. Of course, we still have the condition on the right? That didn't really go away. So the sum over alpha I yi equals 0. We still have the condition alpha I greater or equal than 0. Now, trick question, what happened to that first condition, right? So, we still have to deal with this one. That's that one here. We have this one because they're Lagrange multipliers. Where did this one end up? Any suggestions? W disappeared. And so, but why don't I still have to carry that constraint around with us? Yep.
It's incorporated in the objective function.
It's incorporated in the objective function. And furthermore, and that's, it's automatically satisfied for any choice of the alphas. So that's why I don't have to worry about it. I plugged it into the Lagrange function, sure. But more than that, for any choice of alphas, this condition can always be satisfied, so I don't really have to worry about it. So that's a useful thing that you sometimes can do if you want to solve those optimization problems. So remember, Geoff already talked about primal and dual objectives, primal and dual constraints, and the Kuntaka conditions. And as it turns out, you can, rather than minimizing the primal or maximizing the dual, well, let's turn this entire thing into a problem of just solving the constraints. So basically, these two constraints and these, and also require that the Kuntaka conditions are satisfied. This is what's called an interior point solver. And for probably about 1 or 2 decades, I mean, even now they're still very, very competitive solvers. So let me just write out the name. So they are some of the easiest to implement, actually. As in, this is like maybe about 100 lines of code. And they actually work very well.
They're the analog of Newton's method for constrained problems.
So in Newton's method, you basically solve the equality constraint f prime of x equals 0. And in the more general case, you basically solve that type of constraints for the primal and the dual. So this is strictly the generalization of Newton's method. Okay. So let's look at SVMs again. We had this as a dual. And by the way, sometimes you've probably seen the SVM dual not as a maximization problem, but as a minimization problem. And all you do is you just flip the signs in the objective and you're done, right? You minimize 1/2 of this plus that. Okay. And so we also have those Karush-Kuntaka conditions at optimality. It's kind of interesting. So Karush was the first one to actually come up with those, I think in 1934 or 1943. I don't quite recall which of those years. This was part of his master's thesis, right? It then got forgotten because people had, more horrible things to do to each other. This was during the Second World War. And then Kuhn and Tucker came, essentially rediscovered this in the 50s. And for a long time, they were known as the Kuntaka conditions. And only later, people realized, well, this master student almost a decade earlier had it too. And so that's why I think it's fair to call them the KKT conditions. In any case, what I mean is that if you look at the Lagrange function, that constraint times variable, that expression has to vanish. So constraint times variable in our case is exactly alpha I times yi times, w dot xi plus b minus 1. So we know that optimality vanish. Okay, so what does that mean? It means, actually, any suggestions of what that constraint means? And don't look at the next slide. Okay.
We either have AI0 or the constraint, which is the constraint is a support vector.
Correct. So it basically means that these alpha i's can only be non-zero whenever this vanishes. Right? For any other case, this can, basically the alpha i's must be 0. So if the constraint is strictly satisfied with a strict inequality rather than an equality, then the alpha i's have to be 0. So those points can never show up in the expansion of the support vectors. So that's exactly the same thing as what we had in the perceptron, except that in the perceptron we went through it, and you could still classify the point correctly later on, but we only had to encounter it as a mistake when we actually saw this point. Here, what you're imposing is that the point needs to be, so only those points that sit exactly on the boundary can actually even enter the entire expansion. The other nice thing that happens from this is that, of course, now the entire problem is dimension independent. Doesn't matter how high dimensional the x's were. Initially, you get an expansion of w in terms of them. And furthermore, the optimization problem now only depends on the number of observations that you have rather than dimensionality. So you really only have inner products. This is kind of a cool thing. It's the same property again as what we saw with the perceptron. And this turned out to be an extremely useful fact if you wanted to make these algorithms nonlinear. Because all you had to do is just, under the hood, replace the x's by phi of xi, or phi of x, and then you immediately had a nonlinear algorithm. With all that talking, let me show you a few examples. So here's some data points, and lo and behold, these are the support vectors, and you can see nicely color-coded, how the data is to be separated. Okay? Now, why do you care about large margins? You also make it so that you take observations and make them put larger and larger balls around them, and you want to find the hyperplane that still separates them for as large balls as possible. That's good because it basically means that you have some leeway getting the measurements of your observations wrong, and you still get the classification correct. Okay. Yep.
Are there generalizations of this if you think your error is not spherical around the observations?
Very, very good question. That unfortunately leads to, if you're lucky, second-order cone programs. So there's a paper that we wrote with Chiranjeev Bhattacharya and a few others on that very issue. The math gets unpleasant. You can write, a paper about it, and you can derive a lot of nice things. In practice, what you would probably be best off doing is actually solving this with a constraint generation approach. So if you want to know more about that, maybe let's talk about it offline. We were more excited about the math at the time than in an approximate way, fairly efficiently, essentially generating constraints in a stochastic gradient descent approach. But yes, you could have other shapes around it. So there was also, for instance, a best paper prize awarded to Olvi Mangasarian and I think Glenn Fung, where they said, well, we know of certain regions of observations which are to be classified in certain ways, so let's constrain the optimization problem further. So let me show you what happens is, so usually you would have, let's say, these points, and maybe, okay, let's say you have these observations, you want to separate them. Then what you could say is, well, in some cases I know that this entire region here is actually also full of circles, and so then you get the large margin separator that separates entire regions. The problem is actually, if you already have that as a prior knowledge, it's kind of stupid to try to relearn your prior knowledge in some other way, and you can actually doing this and then just making an exception for that set. Follow up that we wrote at some point. Because you can basically just happily ignore those. But it's a good question. So for some time, people were actually playing around with those constraints quite a bit. Now, the one thing that's obvious is, well, what happens if I get even just a single point wrong? Because you could end up with an optimization problem that does not have a solution. So if you recall this situation here, right? I said, well, this region here is actually feasible. All I need is just a single point which says, well, no, everything has to lie on this side. So then this destroys everything here. And you're left with, okay, besides the fact that it looks like horrible scribbles, basically no set of variables that actually can satisfy all constraints at the same time. And so you have to find a way around it because reality may quite often give you slightly contradictory labelings. So this leads to what's called soft margin classifiers. And the peculiar fact is that it took until 1995 for people in support vectors to realize that, so that's the Cortes and Wapnick paper. And this happened only after, in mathematical programming, for an L1 type margin. This was done by Bennett and Mangasarian in 92. So basically for about 3 decades, nobody really made decent progress on that problem, which is kind of fun, right? It's such a simple thing. So if you think about it, this is actually a very common case that you have at least, some piece of, let's say, green spam that, should be on the wrong side. That's on the wrong side. So what to do? Because, you can clearly not find a linear separator. And as a matter of fact, there's a theorem by Minsky and Papert which says that finding the minimum error separating hyperplane is NP hard. So it's kind of weird, right? So I'm telling you, well, here's an algorithm that will deal with cases where you can't really separate things optimally, and it's a convex program, and so therefore, you have a polynomial time solution and all that. And then there's this result by Minsky and Papert, which tells you, well, no, you really can't. This is exactly the thing that I referred to before a couple of weeks ago. Always read the fine print of impossibility theorems. So what actually happens is that, yes, finding the minimum error separator is NP-hard, and you can construct cases where it's really basically, where you're exact in the boundary, and if you get this one right, the other one gets wrong, and you need to figure out exactly which way you tilt and wiggle things. And you can make life bad for yourself. However, if you allow for a slight amount of ambiguity, namely number of points exactly on a boundary, then the problem all of a sudden can be solved in polynomial time. We had that same problem again later on for novelty detection. It was kind of fun because Scheibe and David proved the result that essentially along the lines of Minsky and Papert, the hardness result. And we had an algorithm which gave a novelty detector, and the talks were back to back. We didn't know of each other, of having those results. And then afterwards, we looked at it, we were very confused what's going on. There's an impossibility result, and here's an algorithm. And the same thing happened again for clustering. NIPS in 2 subsequent years on the impossibility of clustering, and then actually a modification which showed that it was possible. Again, a slight change in the constraints in the definition of what considers hardness can turn a problem from hard into polynomial time. And often in practice, you won't care very much about that little detail in the constraint change. So there's a good chance that if you have a hardness result, and there's an algorithm that works really well in practice, that maybe in proving the hardness results, people assumed a little bit too much, and it may be in a very innocuous place. Anyway, so let me show you how to do this. So let's set up the convex optimization problem. So you have w of x plus b less equal then -1 plus psi. So if I add psi to that, and psi is just what's called a slack variable, then of course this is. And likewise on the right-hand side, if I want to satisfy it, I just subtract psi from it. If I make psi large enough, then I can always do it. Right? Now, this unfortunately changes things a little. Rather than finding a large margin separator, well, I also want to minimize the amount of slack between the data sets. Right? So, if I classify a point wrongly, I have to pay. And now, I just want to make sure that, I don't end up paying too much for it. So we can skip over the next slide because you've already done that to a large extent last week. So let's convert the optimization problem. So before that, we had minimize 1/2 w squared under the constraint that y equal than 1. Now what we have is we have the same constraint as before, except that we add the slack to it. So if we'll subtract it from the 1. So if I do this, well, I can always make this psi I large enough that I can satisfy these constraints. Can somebody tell me a feasible set of parameters right away? So exactly, psi I equals 1, and w and b equals 0 will always be feasible. So what this immediately does shows that there is a set of parameters for which this optimization problem at least is well defined. This is almost certainly not the optimal solution, but at least it's a set of parameters which shows that the domain is non-empty. Okay. Now, of course, I have to pay for my slacks, and I have to pay C for them. So depending on now how large I make C, the harder the optimization algorithm will try to make those slacks very small, then the algorithm will be be very lazy and just try to, just do a sort of kind of okay job in separating things. Yeah, that's the feasibility. And well then, what we do is we just crank the handle again on the Lagrange function. Any questions about the slack so far? Yes?
So can you use slack as a measure of your misclassification?
It's a good proxy for that. It's not quite the same thing, but it's a good proxy. So what we'll see later on is actually the following. If you look at yi f of xi, so that's basically the score from my classifier, this would be a measure of misclassification. Right? It's basically 1 up to the point 0 and then 0 thereafter. Right? So that's basically if I get the sign wrong, I make a mistake, otherwise I'm fine. What will happen is that the slack will actually be a convex upper bound, and the function, the loss function, will look like so. If the words loss function and so on don't really mean much to you yet, don't worry, we'll get to that eventually. And I'd actually on Wednesday I'd like to have a short show of votes of what you would like us to cover in the weeks thereafter. Because we can basically do more Bayesian methods, or we can go more into theory and prove uniform convergence bounds and so on. Both of those are really useful for machine learning. One will help you more understand why some things work. The other one will help you a little bit more solve them. And we'll get both eventually, but we can emphasize one or the other. We can emphasize understanding or doing. And that's largely up to you. But it's a very good question. So the slack variable, as we will see later on, is going to be it's going to be an upper bound on the number of mistakes that I make. But it's not the same. So especially here, the slacks can be much larger than the mistakes, which at some point led to do this. Right? And this actually gave them a best paper prize. Small side note, we discussed a similar idea and we said, well, that's too simple, they'll reject the paper. So we didn't even publish it. We then published a really complicated follow-up, but yeah. Yes, this is not convex. That's true. And there are tricks on how to solve this non-convex problem. So just a brief aside, and then we need to, well, yeah, okay, well, there's no time anymore to do the dual problem anyway, except that you might well look at that at your leisure until Wednesday. But basically, if I have a non-convex problem and I want to solve this, so there is a method that's been invented at least 4 or 5 times. It's called DC programming. It's called the M method. It's a special case of the EM algorithm. And it's also called the constrained concave and convex procedure. And they're all for the same thing. Those are the 4 cases that I know of where it's been essentially reinvented. And here's the basic idea. I have some function which is non-convex. Well, I know that if this function was convex, my life would be really easy, right? Then I could just minimize this function here. Now I can go and write it as this plus some concave part. Okay. Now what I can do is I can say that this is, of course, less equal than that plus that, which is a tangent on the concave part. Right? It's an upper bound. So now I can go and minimize the sum between this convex function and the linear function, which is convex, of course, the sum of those two. And that gives me a new upper bound. Let's say I end up here. I now, at this new point, go and compute the new tangent. And well, I go and compute it again, and I keep on doing this a few times. And at each step, I make progress. I make progress whenever I minimize, because, well, I'm minimizing an upper bound, so therefore the true function also needs to go down. And I make progress whenever I recompute the tangent, because at that point I'm evaluating the function exactly. And this is what's behind all those algorithms, including the EM algorithm. So the EM algorithm, computing the tangent actually amounts to taking expectations over random variables. Don't worry, we'll get into this, we'll get into it in detail, so don't be too scared. But just because you asked, how do you solve a non-convex problem, here's a very simple way. And that's precisely what those guys did here in this problem. What they did is basically the following. They ran the SVM classifier, as you would. And then they threw out the points that were significantly misclassified. And they just reran it. And at each time they checked which points are significantly misclassified or not. And by this simple argument that I showed you here, you can then prove that this algorithm, which sounds crazy at first, actually converges. And that was that. Okay, so I think I've gone 2 minutes over time. And I'll see you on Wednesday.